Good morning. Announcements. Midterm 2 is this evening, right? 6 to 7:30 in Lecture Center A1. Same place where the first one was. Arc Lab is due Thursday night. Homework was due yesterday. Any questions? Yeah.
So for number 3, it seems similar to what we had to do on the homework, except we're not given the number of instructions. How do we go about that differently from the homework?
So the question was, question 3 on the sample midterm is looking for you to calculate the CPI for a program, and we give you the percentages. You don't ever need to know the exact number of instructions, right? If you know the percentages, that's enough, right? Does that make sense, right? So I mean, so how often, like the question that you have to ask is, how often do we have a load use stall? That's the question that you have to ask, right? So given the information that we're provided, do we have enough information to calculate that? We know that 20% of the instructions are memory to register moves. We know that there are no pop instructions, right? Those are the two instructions that are going to cause that load use, right? We load it into memory. Pardon me, we load it into the processor from memory, and then we immediately use it, right? So we know that 20% of the instructions are going to be loads, and we know that 40% of those are followed by an instruction that uses that data, right? So that information tells you how many load use stalls there's going to be. Does that make sense?
Yeah.
Right? So for that particular piece, let me grab it. Well, why don't we solve the whole thing just so that we're all... Right, so this bit with this are load use. We also need mispredict. And then what's the other stall that we might have to deal with? The returns, right? And so how many load use, or again, what we don't really know, we don't want to know how many load uses there were. We want to know how many stalls get added to our ideal, right? And so if we know that 20% of the instructions are memory to register move, and we know 40% of those are followed by an instruction that just uses it, what do we do with that information? We're going to multiply them, right? So we're going to take 20% times 40%. That's how often there will be a load use stall. And how many cycles do we have to stall? How many stalls do we have to have for a load use? Just one. One cycle. And so that's the contribution that's going to increase the ideal CPI, right? And what's the ideal CPI again? 1. Our ideal CPI is 1. Each instruction should just take 1 cycle, but these stalls are going to be the thing that's going to increase that. Okay? So why don't we do the last two pieces, right? The return penalty or the return stalls, how many of those do we have? Right, 5% are returns. And that one's going to be 3 stalls. And then what about the misprediction stalls? So 25% are conditional jumps. How many are mispredicted? 40%. And how many stalls are we going to have? 2. Right? Now, again, it's kind of, it's for this particular problem, I agree we don't need to know more than just those numbers, right? But it is totally fair game to say, hey, draw me why it's 2 stalls for a misprediction. Right? Draw me the pipeline diagram that illustrates why it's 2 stalls. Right? And in my opinion, going back to that pipeline diagram is the thing that will save you, right? Whether it's 2 or 3 or whatever. I mean, again, I could change the problem, right? If we change the problem and say there's 6 stages in our pipeline and we move things around a little bit, you've got to understand where that number came from so that in the new situation you can figure out what that looks like, right? But for this problem, we would then add these all up, right? So we're going to add this plus this and a 1, right? So this is the ideal, right? And then that total is the CPI, right? And again, just before we all freak out, there are no calculators on the exam, right? This is fine. You can leave it in this form. This is a closed form. It describes all the values. I don't need the decimal value. If you want to do the decimal value and you want to write it out, you're one of those people, that's fine. You're more than welcome to do that, right? I mean, it's easy to grade that as well, right? But that encompasses the answer just as well. Any other questions on this? Yeah. Yeah, so the question was, what do we do with the other information that's in here? So we found out that 5% of the instructions are calls. Do we have to stall the processor because of a call? So we're at ideal of 1 for a call. Do we have to stall for the arithmetic instructions? Not normally. We've got forwarding, they're all going, and so that's in the ideal again, right? We are just looking for the places that are going to deviate from ideal, the places where the pipeline has got a stall. And these are the 3 in the one that we discussed in class. Other questions? Yeah.
Could we go over question 7?
Question 7. Okay, so question 7 says, for the following y86 instruction stream, draw the pipeline diagram as shows in each cycle where each is divided. Assume the base pipeline processor with all possible forwarding paths and the 5 pipeline discussed in class with fetch, decode, execute, memory, and write back. So here we need this. This. Okay, so the first thing when we're looking at this, what do we want to do? What should we do? Yeah, we want to start with some cycles, right? And while we're doing that, what do we want to look for? We want to look for data hazards, right? And so people are shouting stalls, and I'm like, yeah, we're really interested about the stalls, but the stalls are created because of this data use, right? Or a mispredict, or a load use, right? So those are all the reasons that we're going to have this. But the load use comes about because there's a data hazard that one instruction produces the result and the other one needs it. The mispredict comes about because of a conditional jump that we don't have. We don't have a return, so we don't have that one, right? So we're really just looking at data hazards here for this particular instruction, right? And so where do we see data hazards? Between instruction 2 and 3 on register RCX. No, there's no data hazard there. Between 1 and 2 on instruction RBX. That is the lone data hazard that we have, right? Now, why is there no data hazard between 2 and 3? I agree that both of them are using RCX, so don't get me wrong. I can read RCX in both of those instructions, but is it a data hazard?
No.
Why? Why is it not a data hazard?
RCX isn't changing.
The push instruction is not producing the value in RCX. The push instruction is taking the value in RBX and using the value in RCX as a pointer and saying, go place this out in memory. RCX is not going to change as a result of that instruction. Thus, when I want to use it in the add immediate instruction, there's no problem. Right? There's no data hazard there. We're using it, right? So when we do this, the first instruction, do we need to do anything? Do I need to worry about hazards or stalls or anything when I do that first instruction? No, I don't have anything above me. I'm assuming this is the first instruction. There's nothing to worry about, right? So that one just goes through the pipeline as expected. Ideal, right? It goes through each of the 5 stages, right? The push instruction is going to start on what cycle? The push will start here, right? And ideally, we'd like it to do this. Ideally, we would like it to do that. And is that what happens? Why? Why is that not what happens? RBX is not available until cycle 3. RBX is available here, but we need it here, right? And so what we need to have happen is that we need this to be the execute, the memory, and the write back, right? That's what we need to have happen. Now, again, students get a little caught up. They're like, well, how do I exactly draw that stall, right? Should I stay in decode? Can I stay in execute like this? Do I write stall? Do I write the word stall out? Do I leave a bubble? It doesn't really matter, right? I mean, it's just whatever makes you feel good, right? The key is that in cycle 4, that instruction is in execute, right? And any instruction that follows it can't move past it. Right? So whatever you do to instruct the second instruction, that push instruction, has got to also be shown in the third instruction. Right? So if we say that the third instruction starts here and is in fetch and then goes to decode, we can't have it go to execute. Right? I mean, you can't do that because there's already something there, so it's got to stay here. Right? Again, the idea is that it's stalled, right? And that nothing else is moving on. Right? Now, again, if your question is, hey, but reality pipeline, and what does it really look like, and how does it really work, that's great. We could talk about that, right? But this problem is there's only 3 instructions, just a little snippet, right, to understand the concepts that are going on, right? Okay? Comments, thoughts? Yeah.
Near the beginning of the chapter, it says top Q is just top Q and then 1 register. This has 2. I was just wondering why the book would.
Yeah, so this is the prof not paying attention on the problem, right? So in reality, the instruction should just have been pop RBX and push RBX. Right. I mean, that's, right. Yeah. I try very hard to be consistent. It doesn't always happen, right? So yeah. It should really have been pop RBX and push RBX and then add immediate Q RCX, right? So I'm trying to, yeah, I agree. Thank you. So any other questions on this one, right? And again, on the exam, if there's something that you're like, wait a minute, I'm not quite sure, this doesn't feel right to me, just raise a hand, talk to me. And I want to stress, the TAs are trying really hard, but if they give you an answer that you don't like in the exam, come talk to me, right? The buck stops with me. If the TA is like, you have everything that you need, good luck, that's, that's not helpful, right? I mean, it's not that they don't know what to say. It's just they're uncomfortable giving away too much, maybe, or whatever. So again, you know, I'll be in there. You're welcome to come talk to me. I'll have a couple TAs to help, but you know, yeah. Number four. You want to create a new instruction that has, that we want to replicate the LEAQ instruction from x86, an example. And so I gave you the addressing mode and everything that you need to have, and then detail what's going to happen in each of the 5 stages, right? So let's, so we want to do an LEAQ for RDI RCX, right? And so. Okay, so, and again, the RDI RCX is just for informational purposes. It's not an end-all, be-all or anything, right? Also, I'm not too concerned or you don't got to get overwhelmed of, you know, am I using RA or am I using RB? Which one is in which field, right? I mean, you're using both of them, right? I mean, it doesn't really matter for this particular instruction, but you know, if you're off on one or the other, it's not the end of the world, right? Your processor just got a little more complicated, that's all, right? So when we look at this instruction, this is kind of, it's a 2-part piece, right? We need to know what's happening in fetch during our pipeline, and then we need to know what's going to happen for this particular instruction, right? So what is this instruction going to do during fetch? It's going to fetch iCode and iFun. So it's going to fetch iCode, iFun. And if you want to write it out in a sentence, or if you want to use the notation that they use in the book, those are both exactly the same. Again, I prefer people using their own words, right? But again, if you're memorizing things from the book, that's fine. As well, right? We're going to go out to the memory. We're going to grab the address, the value at the address in the program counter. We're going to stick that into iCode, iFun, right? What else are we going to do during fetch? We need RA and RB, right? That's the next byte, right? So we're going to get RA, RB, and again in the other it'd look like this. The only benefit that I see, or one of the benefits that I see to using the notation from the book, is that it's going to help you figure out how big the instruction is, right? Because you need to keep thinking about how big each of these fields are and where they're at and how we're getting them, right? What else do we need to do? We need to get val C. Right? And then we also need to do val P. And how big is the instruction? 10 bytes, right? So we got to add 10 to that, right? We got 1 byte for iCode iFun, we got 1 byte for RARB, and we got 8 bytes for val C. We said all of our displacements or addresses or the constants were going to be 8 bytes. Anything else in fetch? So what's going to happen during decode? We need to get the values, so we need to get val A, val B, right? We need to get those values. We don't really need RCX. We don't need the value of RCX, right? But the hardware may do both anyway. The hardware may just get both values and then just ignore one of them, right? Also, if you're really concerned, right, if you're really following the details of the book said, look, there are no instructions that use val A as well as val P, and we merge those. And, you know, don't worry about that. We have to modify the processor to add this particular instruction, right? So I'm not looking for anything tricky like that. Anything else that's got to happen during decode? I think that's it. What about execute? Huh? Yeah, we got to calculate the address. Calculate the address, right? And so again, it's going to be 4 plus RDI. And what do we expect? Maybe we ought to take a step back to the fetch and specify, where do we expect RDI to go? Do you think it's going to be an RA or is it going to be an RB? You think it's going to be an RB? Why do you think it's going to be an RB? Where do we store the result? Where are we going to store the result? We're going to store the result in whatever's in RB, right? That's the way that we've always set this up. And we're going to store this into RCX, right? So again, I agree. This is changing a lot of our conventions that we're used to, right? We saw that all the instructions that used the offsets and went to memory, they put RB inside of there. I get that, right? But sometimes we got to, it's not the end of the world if you switch it either way, right? So again, I'm looking for a calculate the address, 4 plus RDI, and this is going to go into val E, right? That's the critical part. What happens during the memory then? Does the LEAQ actually go out to the memory and get the value that's there? No. Right? So the memory, we're not going to do anything. And then in write back, what's going to happen? Right? RCX is going to get val E. And is this particular instruction going to cause any stalls or anything? Right? Like if there was another instruction right after this that used RCX, do we think that this one's going to, would that cause a stall? Is that like a load use or anything? No, right? Because the execute, we have the value that will eventually be in RCX. We can forward it, and it'll be to execute again. So we should be okay in that sense. Other questions? Yeah. Number 5. So this is our the last little bit of chapter 3, if you will. So we've got this memory with this struct. And the question asks, give the address of where last name, first name, and the next variables are stored in this particular, or for the one starting at 1190. So we tell you that there's a node here, and so we want to know the address of last name, first name, and next, right? We want to know those addresses. So where is last name? Where does it start? What address? Like if I was sending this to printf, I'd need the starting address, right? So where is the starting address of that array? It is exactly what I underlined, right? So it starts at 0x601190, right? Last name starts at the beginning address of that whole node, right? That node and last name are going to share that starting address, right? And then where is the starting address of first name going to be? Is it 20 bytes after? Well, that's kind of the question we're asking, right? That's what we're I agree that this is going to take 20 bytes, right? So how many bytes are here? That's 8. That's 8. And then 1, 2, 3, 4, right? So this is... I need that other 0. There you go. Right? So those are the 20 bytes that make up last name. Right? But where is first name? That's what we need to know, right? So are there any restrictions as to the address that first name can start at? Do I have to worry about alignment with characters? Do I have to byte align, word align, 8-byte align? No, right? So I can start at that very next character. So that 70 is the first character of first name, right? And so first name is going to be that 4, those 8, and those 8. So first name is going to start at 0x6011A4. Yeah.
Can you explain again how you're able to distinguish like the beginning of last name?
Could I specify again how I knew the beginning of last name? So we told you that the node started at address 601190. That's the beginning of the node. It said that in the text, right? Huh? Yeah, above this, right? So if we go back to the exam, right? Right? Starts. We said it started at that address, and then we gave you the snapshot of the memory around it. So we know that it starts at 1190. That's where last name is. Then we've got to go 20 bytes out to find the beginning of first name, and then where is next going to be stored? Okay, that one's going to be, this is next, right? And it's at 6011B8, right? And again, I don't want to know what's in the value. I want to know where the value is, right? That this particular question asked, where is it, not what is it? Okay? Yeah. No, first name isn't 4 bytes, right? First name is 20 bytes, right?
Yeah, so like, I'm not too sure why it's A4.
Do you agree that the red portion is first name? Yeah. So what's the address of that first byte? Right? This here is the first byte of first name. So what is the address of that byte? Right. I got to skip 4 bytes, the last 4 bytes of last name, and so it's A4. Yeah. Okay. What else did the question ask for? The question said, give me, what did I want? Give the address of where the first and the last character are for the first name C string associated with the node starting at address 601190. So first name is the second piece, the address. Right? So the first character is at this address. The last character And so where is the last character at? Would it be A8? So, yeah. So again, we need to be careful with this, right? And I was thinking about that as I was looking at this, right? So, the data does not use all 20 bytes, right? And so the last character, and I guess that gets kind of tricky too, right? Do you count the null character? Because that 0, 0 is the null character of the C string, right? So I could see that if you're looking for where the null character is, that would be at A9. A9, that's the terminating character. The last 6011A8, that's the 0A, that's the last character in the string, right? The last character in the total 20-byte string is at what address? B7, right? That's the last of the 20, right? I think my original intent is I was looking for the B7, but again, I can rationalize the other two answers as well, right? Does that make sense? Yeah.
I thought 0A was the new line character.
It is.
Okay, so does that count as is that included in the C string?
Ah, is that included in the C string? So when you print out the C string, does it move to the next line or not?
Yes.
Yeah. Yeah. Right? So again, it's this. I mean, these are all the realities that we learned about in 141, right? We know that, hey, sometimes that new line gets in there and sometimes it doesn't, and do I care, and do I want it, or do I not want it? And now this is the physical reality of it, right? That it's there, right? And that new line character is there, and then I've got the null character at the end of it, and then there's more space that I could have used, right? Yeah. What else? So that, how many of the 4 nodes are shown in the memory dump? How many nodes do we see? There is no other node shown on the screen, right? There is nothing. Where is the next node? What's the starting address of the next node? 601110. Right? Do I see 1110? It's up higher, right? So again, this was not, yeah, so I don't see the next one. And the zeros at C0, that's not, there's no, I definitely don't see a whole node, right? Because how much space does the node take? Right? The last name and first name are each 20, that's 40. The pointer is 8, so 48 bytes, right? 6 8-byte quantities. Okay? Yeah.
Can you explain why they put in C0 why that line is just full of zeros, for C0 and C8?
Yeah, so why did the operating system, or where did this stuff come from, right? And so we said before when we were doing these things, we had to be very careful because there could be stuff left over, or the operating system could be giving us stuff we really don't know, right? So in this particular instance, that last line with C0, I don't know why the 21 is there, right? I mean, I know that it's not part of my node that's at 1190. It's definitely not part of that node, right? My gut instinct is always saying that the operating system, even though we only need 48 bytes, it may give us more. Maybe it doesn't like mallocing 48 bytes. It likes mallocing 48, 54, 60. It wanted to do 60 bytes, right? 64 bytes, 64 bytes. So it did 64 bytes. And it put that 21 as a marker, kind of as a token to say, hey, if this changes, something's wrong, right? Because nobody was supposed to touch this, and it changed, right? And so we'll look at that a little bit more after the exam too, of why these values might be out in the memory and what their significance is, right? But that's always been my understanding, is that even though the data structure needs less space, the operating system, when it's mallocking and giving us the memory, may do it in larger chunks, right? And again, we're not worried about the operating system here. That's 361, right? That might be a good question for there as well, but we have to see it, right? And again, I'm just pulling data, right? I just type it and grab it out of GDB. It should have been what we saw in Bomb Lab. It should have been what we saw when we were looking at the problems, right? Yeah.
So just to clarify, how large is that struct?
That struct is 48 bytes.
So the pointer is 8 bytes. I understand that.
Yeah.
But as far as the last name and the first name array, isn't like a single char supposed to be 4 bytes?
Nope. Single car is 1 byte. Yeah. ASCII code, 8 bits, right? 0 to 255 is our ASCII table. Yeah. Number 2. Yeah. Any other questions on this one though before we bounce off? Okay. Give a y86 code instruction that's equivalent to the following x86 code. So, okay, so the first thing we need to know, and again, this is why it's kind of cumulative, right? We need to know what the x86 addressing mode is doing. And we also need to know what LEAQ is doing. You'll notice that it appeared a couple times on the exam, right? So what is ignoring the pipeline, ignoring the y86 instructions, ignoring all of that, what is this instruction doing? Yeah, so that's the end result, right? That's what we need to have happen, right? Now our question is, what do we use, how do we use y86 to accomplish that, right? And I would also point out, it'd be really good if we do not destroy values that we shouldn't, right? So things like, does the instruction as shown destroy R9? No. Does the instruction as shown modify the stack pointer? No. So it would really be good if our instruction stream did the same, right? Now I totally get it that, hey, we may have issues. There may be ways that we've got to destroy a register value. I totally get it. But hopefully we can do it all in RCX, because that's the one that's going to change. And so we should try, it doesn't always happen, but we should try to think about the operations that have to happen and make sure that we do not destroy anything else other than RCX, right? And again, it just depends where you're at in that spectrum of knowledge, right? If your base understanding is, I just need to do RDI plus RDX plus 4 and get me the heck out of here, that's fine, right? I totally get it, right? But that's the next step, right, is to make sure that we don't destroy RCX. So what do we need to do then? Yeah, so we should take that immediate to register and we should move it to RCX, right? We're going to stick the 4 into RCX. Then what should we do? Add RDI RCX. And again, the order of operations is not really important, but then we're done. Is that the only answer? No, right? And it's fair game. You know, we had you implement add immediate into the y86 instruction set. If you wanted to use that in this problem, that's fine. You're more than welcome to do that. And if you wanted to do that, it might look something like register to register move. I want to move RDX to RCX. Then I can do add immediate for an RCX. Right, and then an add queue. Right, that's fair. That's valid too. Right. Other questions? Yeah. Number 1. Give the number of stalls, bubbles that will occur in our pipelined YD6 processor for the following 2 sequences. You can assume all the forwarding paths are available in the pipeline. So let me grab these real quick. Okay, so if we're looking at the instruction stream on the left, let's focus on that one initially. Where are our hazards? What are the data hazards that we have to deal with? What are the load use hazards, the mispredictions, the return penalties? What all those do we have? POP has the potential to cause problems if we immediately use RDX in the next clock cycle, which we do. And so what is that going to do? 1 stall. Yeah, and then let's see, is there a stall between these 2? There's no stall there. And then what about this one? Register to memory move. So we produce the value in the add, we immediately use it in the register to memory move. Again, how can we verify it, right? So if we have the add, fetch, decode, execute, memory, write back, and then we have the register to memory, fetch, decode, execute, memory, write back. The value is produced there, the value is needed there, we're all set, we just forward it, right? And so this one is only going to produce 1 stall. And again, I get that that's difficult, right? I mean, you see these 4 instructions, and you're like, oh, he's going to give us all these stalls. He's going to give, right? You got to be able to look at that and know when we're going to stall and when we're not going to stall, right? It's not all doom and gloom in reality, right? And then what about the instruction mix on the right? The return is going to cause problems for sure, right? Will we ever get to the add? No, right? Maybe that add is part of another function. Maybe it's a label. Maybe it's right. I don't know, whatever. We're not going to get to that add after the return. But there will be 3 cycles of stall as a result of this, right? So there's going to be 3 stalls here. Any others that we need to worry about? Yeah, what about this one? Does this cause a problem? Do I immediately use it? No. But I use it here. Yeah, so the load use is only a 1 cycle stall, and so that 1 cycle I stuck that add Q in there so that shouldn't cause a problem. I should be able to forward the result, right? So again, in the pipeline diagram, if you drew it out, you'd see fetch, decode, execute, memory, write back, fetch, decode, execute, memory, write back, fetch, decode, execute, memory. So here, when we go to this execute, we see that, hey, that value of RAX is available, right? So we can forward it, right? We can just forward it. So if the instructions were switched, right, if the add and if the 2 adds were switched, we'd have a load use, but because we put them the other way, we don't. Then we have the return. We never get to the add Q, RCX, RBX, and they're not causing any hazards either. So, right, and this one never gets executed. Right? Questions on that? Comments? Other questions? Anything else we'd like to discuss today? 10. Give 2 examples of optimizations other than loop enrolling that can be performed on the following code snippet that would improve the overall performance of the code. 10 points total, 5 points each optimization. So what are some things that we should be looking for? What are some things that we should be looking for? Yeah. Yeah, so we're executing and calling string length A a lot, right? How many times per iteration of the loop are we calling string length on A? Twice. Do we change the string A at all? Are we moving things, changing the length? It doesn't appear that we're changing the string length at all. So both of these can come out, right? Both of these should get moved out, right? Code motion. And so we should see something like length equals string length A. Right? And then we should put length in both of those places, right? What else?
You could decrease the memory calls by replacing the num pointer with like a value and setting num pointer equal to f(n).
So do we need to be modifying the num pointer every iteration? Yeah, probably not, right? Or we don't need to be going to memory with it every time, right? So we could move that out, right? Do we need to be modifying the star B every iteration of the loop? Yeah, because every iteration of the loop, that star B is different, right? It's a different position in the array, right? So again, just because you see the star doesn't mean that you got to pull it out, right? You got to make sure that the code is doing what it's supposed to be doing. We're actually copying bits of A and putting them into B, right? And then num is just keeping track of how many we copied, right? So that could totally be replaced. That's a constant even, right? We know how many times that's going to loop. It's going to be length. We could just do that once at the end, right? Anything else? Anything else? Yeah.
Let's say if you wanted to approach loop-unrolling, would you have to know more about this function before you can do that?
Okay, so the question is, if we wanted to loop unroll this, do we have to know more about what's going on? So let's hold that for one moment. Are there any other optimizations that we can do in this code? Do we need to be doing this math every time? Do I need to do length minus I minus 1 every time? How much does it change from one iteration to the next? It's by 1, right? So again, I could do this with a pointer. I could do this by just incrementing or decrementing by 1 every iteration of the loop. I don't need to be doing all of that math, right? So this would be code reduction, right? Reduction. Right? That's totally going to be a couple assembly instructions. Even after the code motion and eliminating the call to string length, I would still have to take length, subtract I, subtract 1. The next iteration of the loop, I goes up by 1. I do length minus I minus 1 again. I don't have to do all of that. I only got to add 1. Right? So I could totally do that as well. All right, code reduction, simplification. Okay. Any other optimizations? Okay, then loop unrolling. If we wanted to loop unroll this, the goal is to what? If we wanted to loop unroll, what's the goal? We want to decrease the number of cycles per element by amortizing the loop overhead across more elements. And we also want to do what? We want to expose more parallelism, if at all possible, right? I mean, again, if we do it all correctly, we're going to expose more parallelism in this whole mess as well, right? So if we were going to do this, our goal is, let me, how do I want to annotate it? So we would say, let's do this. We'd have for I equals 0, I is less than some new value, I equals I plus 2, right? Let's do it that way, right? I want to do 2 values every iteration of the loop, right? And so if I want to expose, well, why don't we do it this way? How do I access the 2 elements? Why don't we start there? Right? So I need something along the lines that says star B equals A something, right? I need that. And then I need star B plus 1 equals A plus 1, right? I need that one. Then I would need B equals B plus 2, right? I need that. And then depending upon what we're doing with num, right? Num, star num equals, right? So I guess my gut instinct is saying that's loop unrolling, right? Now the question is, did I expose the parallelism that I also want to make sure that loop unrolling did, right? So let me just get this straight, right? That, loop unrolling, I want to do 2 things every iteration, right? And we looked at that on Thursday and said, look, if I just do it and I'm not thinking about it, I'll do it and I'll get very little improvement, right? I will get some because maybe I've reduced the loop overhead, right? Maybe I've reduced the memory accesses, right? I cut out a memory access to num by doing this, haven't I? Right? I cut out 2 of them, I think. I didn't have to read and write once, right? So I'm going to see an improvement, I think. But did I expose all the parallelism that I could, right? So can these 2 lines here, can these 2 lines be done in parallel? Right? That's, in our gut instinct, if I'm looking at the pipeline, the fetch, decode, execute, memory, write back, just the 5-stage pipeline, can those 2 things be overlapped? Is there anything in the second one that's dependent on the first one? Yeah, I don't think so either. So I think we're okay, right? So again, it depends on the operations that we're doing and how we're accessing the items, right? And it could be the issue is in the parentheses what I left out, right? If I'm not careful, I could put something in there that causes me some dependencies, right? But again, depending upon how I fill in those boxes, I should be able to expose the parallelism, right? And so what should be in this top box here? This should be length minus 1, right? If we're really trying to be concerned. And then we'd also need a cleanup loop, right? Or to handle the odd values, right? So this works great if I have an even number of values, right? 2, 4, 6, 8, 10, 12, whatever. Even if I have an odd, then I need to handle that one last element, right? And maybe I don't need a loop. Maybe I just need to handle, I need an if. If I is not equal to length, kind of a thing, right? To check to see if there's one left, right? Right, and so let me just, I think it would be something like if I is less than length, then I need to do star B equals A right? And I need that. If we loop unrolled 4 times, what has to change? The big loop, I got to have 4 elements, right? I want to make sure that I'm exposing the parallelism. The cleanup is now got to be a loop, right? I may have 3 elements left to do, up to 3 elements left to do, depending upon how many there were to begin with, right? Questions, comments? Yeah. With that in mind, how would we answer number 11? In 3 to 5 sentence detail, why loop unrolling, if done properly, would lower the CPE. So we discussed that a few moments ago, right? That if done properly, we're going to expose more parallelism, right? Which means fewer stalls. And then we're also going to amortize the loop overhead across more elements, right? So instead of doing all of the loop overhead for 1 element, I'm doing the loop overhead over 2 elements, so then that CPE goes down, right? Yeah. 6. So given a non-pipeline processor that requires 100 units of time to complete an instruction, B uses the 4 stages as shown, and they include any overhead that's already been added, so they add up to more than 100 units of time, right? So that's very important, right? Don't get confused about that, right? Processor A requires how long to complete 100 instructions? How do we calculate that? 1 instruction takes how long? 100. 2 instructions take 2 times 100. 3 take 3 times 100, right? So this is going to be 100. Can I do this? No, can't do it here. So let's go, here's a problem 6. It's going to be 100 times 100 for processor A. And yes, if we do the math correctly, it ends up being 10,000 units of time. Again, 100 times 100 is just fine, right? I was always one of those that all of a sudden the 0 becomes an A or something. It just, so 100 times 100 is just fine. When we're doing processor B, it's going to be a little more complicated, right? Processor B is the pipeline. And so what do we have to look at here? How long is our cycle going to be? It's going to be 40 units of time. And why is it going to be 40 units of time? That's the largest of any of the stages, right? So the fact that stage 1, 2, and 4 can do it in less than 40 is all well and good, but stage 3 needs 40. It's going to take 40, right? So I always want to do all 4 of these at the same time, so it's going to always be 40 units of time. So it's totally going to be 40 times 100, right? That's part of it, right? Ideal, that's the ideal. And then what do I need to add to that? I need to add just a little bit more to that. I need to add 120, right? You can either look at it that it takes me 3 cycles to start the first one, or it takes 3 cycles to end the last one. However you want to look at it, it should be all good. Right? And that's 4,120. Right? So again, we're seeing a 2.5 time improvement even with an unbalanced pipeline. Right? I mean, this is really unbalanced. If I took the 100 units of time and I divided it evenly, each one would be about 25. I add a couple of units of time for overhead, maybe I should be at 30 at the most, right? But I'm still seeing a significant improvement even with a somewhat unbalanced pipeline. Other questions? Yeah.
Can we just go over 8E?
8E. 8E is saying list the line numbers for the instructions that should not have been started when the pipeline realizes the JG has been incorrectly predicted and the pipeline is implemented to assume that the branch JG is taken. Okay, so if we're looking here at this code, the JG is going to be the prediction, right? And so what is going to happen when we do that prediction? We're going to assume that the branch is taken, and so we're going to start these down here. We're going to start 6 and 7. Let me grab this. So this instruction is going to assume taken. And so we're going to go here next. We're going to go down to here to this instruction next, right? Do we know for sure that we should have taken it? No, we don't know, right? Because this is going to, the JG is going to do fetch, decode, execute, memory, write back, right? This is instruction 2. We're going to start instruction 6, and we're going to start instruction 7, fetch, decode, fetch, right? And when does the JG know that it should have taken the branch or not? Right there, right after execute. Once we've done execute, that's where it's going to do the condition code check based upon and determine whether that jump should have been taken or not. Right? So we have two options. Either these are going to continue, or thrown out. Right? So question E is asking, list the line numbers for the instructions that should not have been started, and that would be 6 and 7. Right? Those are the two instructions that get started, but if it was mispredicted, get thrown out as a result of the misprediction. Yeah?
Could I ask for more clarification on the jump? So you execute, you decide at the execute stage which val P you go down. And it's either, I'm just remembering, I don't remember right now.
Yeah, so during the decode, when the JG, I think we're still talking about the JG, right? Not the JMP, because there's a JMP, right? So, yeah, so the JG, when it moves the decode, we want to start another instruction, right? We got two choices, right? What are the two choices? We can either assume that it's taken or not taken. Do we have the addresses for both of those instructions? Yes, we have both of those instructions, right? If the jump is not taken, we should use val P. And if the jump is taken, we should use val C. So those are the two addresses. And so the question is, which one should we use? And so in this case, in this diagram, we use val C. We assume that the branch is taken. We use val C. After the execute, we would know whether we should have or not. Yeah.
The question comes because maybe I used it too much, but they use, when showing like the diagrams of how each function works, they have the PC counter at the end for all of them because they haven't made the adjustment.
Right, yeah.
So I was wondering, it's not like the PC is being adjusted after the execute stage.
Sure. So again, you got to remember. So the comment was, when you're looking at how they analyze the execution of each of the y86 instructions, it was the sequential processor. The PC update was at the end. At the end of that section, they said, hey, this is really sucky for the pipeline, and they moved that PC update, and what did we do to it? We moved it to the very beginning of the fetch. We took all of that, and so before instruction 6 gets started, right, before any instruction gets fetched after the JG, the system says, oh, that previous instruction was a JG. I'm going to predict taken. I want to go grab the address out of val C and fetch that instruction. Right? So that all happens right here, right? So right here, the hardware says, oh, because the previous instruction was a JG, I want to go use val C and use that as my program counter to get the next instruction.
And it's always graphing those, trying to find them. The two val P or val E. Sorry, you can.
Well, val P and val C, again, are both available at the end of fetch. So when that next one starts, it can just make that decision real quick.
Okay. Yeah. I'll ask more about
Yeah. What do you got?
So with a jump, isn't the next instruction stored in a val P?
So in a jump, so instruction 5, are you referring to instruction 5, a pure jump or?
Yeah. Like
Yeah.
a regular jump and
So a regular jump is the next instruction, instruction 6? Not at all. A regular jump, the next instruction is at label 2, which is instruction 8, right? And that's stored in val C as well, right? So again, when that jump, when that instruction 5 is in the fetch stage, before the next fetch starts, the system says, oh, the previous instruction was a jump. My PC is in val C. I'm going to go grab that value, and it's going to go fetch the instruction 8.
Okay, so this is for so label 2 is stored in val C when you're using the jump instruction.
Correct? Yeah.
Okay, so as far as for the purpose of val P, like I was reading in the book and I thought it was saying that is purpose to like point to the next instruction.
I agree. And again, we got to be careful because when the book said, in that case, when the book said the next instruction, it really meant the next instruction sequentially. It didn't mean the next instruction that would get executed, right? So I totally agree that val P is pointing to 6, and val C is pointing to 8.
So like it's top down, it's pointing to the next line.
To the next instruction, wherever the next instruction is. As long as the instructions are written this way, yeah, it would be the next instruction. So when I'm doing the sub Q, val P points to 2. When I do the JG, val P points to 3, and val C points to 6. And the question is, which one should I have done, right? Yeah. I tried very hard when we were in class to always say the next sequential instruction, not the next instruction, right? Because it's the next one that appears sequentially. It's not the next one that will get executed, right? Yeah. Yeah.
What's 8A? So
What is 8A? 8A is when the JG instruction has completed the F stage, is the address of the next instruction available in the processor. So is it? Yeah. So you circle yes. Right? Yeah.
Like that question, when it says next instruction, does it mean sequentially or does it mean like
It doesn't matter. They're both there.
yeah, but like what if one of the questions says like, I understand for that, like they're both there right now, but like when that wording is so big, what does it imply? Is it asking like, if this wasn't a yes or no question?
Then that's when you raise your hand and you say, what are you talking about, Thais, right? I mean, again, at this point, it's vague intentionally because it doesn't matter. It doesn't matter if it's the next sequential one. It doesn't matter if it's the next executed one. I have both of those addresses, right? One of those two is going to be the one that I'm going to do, and I got them both, right? So the fact that it's vague does not change the answer, right, in this case, right? Yeah. Okay, any other questions on this? I think we covered everything else, right? But if there is, feel free. 9B, consider the execution of the return. B, after which stage of the pipeline will the address of the next instruction be available in the pipeline? Right? So again, here, when we're saying the next instruction, again, we're talking about the next one to be executed, right? Because we understand, hopefully, that the return had to stall. And where is the address of the next instruction to be executed? Where is the address of the next instruction to be executed after the return? Where in the memory? It's on the stack, right? Should be, if all went well, on the top of the stack. The return is expecting it to be on the top of the stack. So during memory, it's going to go get it, and after memory, it'll be in the processor, right? So at which stage of the pipeline will the address of the next instruction be available in the pipeline? That's why it says after which stage, right? So after the memory stage, right? It's available in the pipeline. That's also why we need to fetch 3 cycles. We need to fetch for the decode, stall. We need to stall the decode, the execute, and the memory, because we're waiting for that next address. The address of the next instruction to be executed. Right? Val P is worthless in this case. Right? Val P does have an address of the next instruction sequentially if there is one, right? But it's not what we want at all, right? Other questions? Hearing none, we'll see you tonight. Sure, but if you do that, you destroy RDX. So, like, if I did this instruction, the immediate next instruction could use RDX, and the value didn't change here as RDX, whereas in your code, the value of RDX would change, and that would be bad, right? So that's why I was saying, this would be correct, but you destroyed a register, right? I mean, you're getting the right value, but you had to be aware of that and make sure that you restored it if you needed it later on. Again, if it's just one instruction, it's okay, right? But because of everything else. Yeah.
I think it was the processor A or processor B question. Kind of confused about the B part. So, how do you get the values 40 times?
Yeah, so again, why we said you looked at each of the stages, and whichever one is the longest, that's what the cycle time is going to be.
Okay, so it's 40 and then time is minimum.
Yeah.
Okay, the 120.
Because there's 4 stages, right? So if we're assuming that 40 times 100 says I'm going to get 1 result every clock cycle, right? It's 40 times 3, right? Because I need to get those 3 cycles done, right? Before I get the result. Yeah. Would you realize you want that value?
So, like, I understand how you count 20 guys last year until here.
Yeah.
But then here, how to get this address?
Well, F7 is at A4. That's the address of where that A7 is located. Because it's the 00 is at A0, right? The next one is at A1,
Oh, yeah.
A2, A3. No problem. Yeah.
I had a question about this. You went over it, but I really didn't understand it. I've been really confused the past few days about just these two. So it's the first character starts with A8, so right.
That's A0.
This is A0.
Well, you're pointing that's A0. That's the value at A0. That's still part of last name.
Okay.
Right? Because last name took 8, 16, and those 4 bytes.
Okay, so do you mind going over it real quick? So I'm a little confused about it.
Yeah, so last name needs 20 bytes,
Yeah.
right?